STEM journals. Supplemental. Remote sensing and on-site analysis has taught humanity a lot about our solar system. But one NASA mission from the University of Arizona is taking the next step to unlocking clues about how water and life on Earth may have started, and how it might end.
Brad.
Dante, I've been everywhere. Like, what else can meteorites tell me about planetary exploration?
Good question. Meteorites are basically free space missions. That is, they're chunks of outer space that land here on Earth for us to study. And they tell us all about the earliest history of our solar system. Let me show you one example here. This is what we call a carbonaceous chondrite. And this is the oldest rock that you will ever see. It basically records the first stages of solar system formation. You're looking at some white crystals in there. Those are the oldest solids that formed in our solar system. They're surrounded by a dark matrix which contains organic molecules that we think may have led to the origin of life on Earth.
And how do we know that?
We learn that through detailed analysis of this and samples just like it.
Dante, what is the purpose of you wearing a glove while handling that rock?
Well, when we study meteorites, we're very sensitive to contamination. This meteorite comes through the Earth's atmosphere, lands on the surface of Earth, people pick it up, scientific information gets lost in all of that noise. Our instruments are very sensitive. This is our laser ablation inductively coupled mass spectrometer.
Can we just call it a laser machine?
Sure,
Okay.
basically.
So what does the laser machine do?
The first part is the laser ablation system, and that kind of works like a magnifying glass. You know, if you take a magnifying glass and you focus that sunlight on a leaf, what happens?
It sets on fire.
That's right. Same kind of thing happens to a meteorite. You focus that laser energy down to a very small spot. Exactly. That turns into a vapor cloud. We send that into the mass spectrometer to learn what the meteorite is made out of, like you can see right over here. So what you see here is the polished surface of a meteorite for analysis. Would you like to give it a shot?
Yeah, I would.
All right, go ahead and pick a location to study on that meteorite and hit go. We're gonna line it up and count down to laser firing.
Why are there so many little dots on the surface?
Well, as you can see, you're firing the laser and you're drilling a hole in the surface of that sample. That liberates the material to send to the mass spectrometer where we learn what's inside. Yeah, in fact, the red is the amount of gold, the blue is the amount of platinum, the green is the amount of iridium in that sample.
Wait, gold and platinum?
That's right.
We should start a business. Asteroid mining? Are you kidding me?
Well, you're gonna have to get in line. I'm leading a mission right now called OSIRIS-REx to visit an asteroid and bring material back to Earth for scientific study.
If we're learning all this stuff from meteorites that are coming to us, why are we spending the time and money to go hundreds of millions of miles away to find them?
Well, Brad, we have two problems when we study meteorites. First, we don't know where they come from. And second, we don't know how contaminated they are when they get into our laboratories. But OSIRIS-REx solves both of those problems.
What does OSIRIS-REx even stand for?
OSIRIS-REx is an acronym that captures the scientific objectives of the mission, and it stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith, Explorer.
I'm just gonna call it OSIRIS-REx then.
Sounds good to me.
Perfect. What are you hoping to achieve with this mission?
Well, Brad, we got 5 primary objectives for OSIRIS-REx. The first is to get to the asteroid, map it, and understand its geology. We're gonna then pick a sample site, send the spacecraft down to the surface, and gather that material. We then tuck it into a sample return capsule and deliver it safely back to the surface of the Earth. We study the information we got from the asteroid and the return sample to determine the future orbital path of that asteroid, primarily determine what's gonna hit the Earth. And finally, we use that information to improve our ability to use telescopes to study asteroids throughout the solar system.
That's how I would have done it. So Cassini took 8 years to get to Saturn. How long is all this supposed to take?
Well, Brad, I've been working on this mission for 9 years now. I've got 11 more to go. It's gonna be about 20 years of my life by the time this is all over.
Wow.
So a 20-year mission requires a multi-generational approach, and one of my other objectives is to train the next generation of scientists and engineers to lead missions like this in the future. Let me introduce you to one of my graduate students, John Kidd, who's playing a major role in the development of this mission. And when you meet him, there's something I want you to bring with you.
Okay.
The voyage continues on the STEM journals.